Today we're going to begin a new unit on probability. But before we begin probability, we first have to study the fundamental counting principle, and we'll incorporate a little bit of permutations. Because many probability problems involve counting the number of outcomes to an experiment and event, it is important to develop techniques that will allow us to count the outcomes in the sample spaces that are very large. So we need the fundamental counting principle to do this, and let's illustrate this by a simple experiment. Suppose we have a two-sided coin, heads or tails, and a six-sided die that's labeled with 1, 2, 3, 4, 5, and 6. And we toss the coin and then the die. And we list all possible outcomes as ordered pairs. And let's assume that the first will represent whatever we get on the coin, and the second would represent whatever we get on the die. So order matters. For example, if I had heads on the coin and 1 on the die, I would list this outcome as H1 with parentheses around it. So I'd like you to take a minute and list all possible outcomes. So I've listed the outcomes here. So if the first will be heads, we could get a 2, a 3, a 4, a 5, or a 6 on the second outcome for the die. And if the first is a tail, we could get a 1, a 2, a 3, a 4, a 5, or a 6. So altogether, we have a total of 12 outcomes. And let's introduce a few definitions. The list of all possible outcomes that can occur in an experiment or an activity is called the sample space. So let's define it here. Definition: the sample space, which we usually denote with a capital S, of an experiment or activity, is the set of all possible outcomes. All right, so in the do now, what we've done is we've just listed all the elements in the sample space. So notice that we can denote the number of elements in the sample space. This is read N of S. This doesn't mean a multiplication symbol. It's just a notation. This means the number of elements in the sample space. So in this case, N of S in the do now is equal to 12. All right, now before we talk about shortcuts, there are various ways to represent the sample space. One way to represent the sample space is to make a tree diagram. And another way to represent the sample space is to make a dot diagram. And I'll talk about these individually. Okay, with the tree diagram, what we do is we make 2 branches for the possible outcome of tossing a coin. So that could be heads or tails. When we toss the die, we have 6 possibilities if the first one has to be heads. So we make 6 branches here. 1, 2, 3, 4, 5, 6. And 6 branches down here. 1, 2, 3, 4, 5, 6. And we label the outcomes 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. And we write the outcomes as ordered pairs at the end of each branch. So the top branch is heads on the coin toss, 1 on the die. Heads and then tails. 2. Heads and then 3. heads 4, heads 5, heads 6, and then if we have tails on the first coin, we have tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. And again, we have our 12 outcomes as we listed in the do now. A dot diagram might be a little bit easier to represent. What we do is we make a grid, like the first quadrant of your graph paper. And we'll say that this horizontal axis is the coin, like the x-axis, but I only have heads or tails. And the vertical axis will be the die axis, which would be 1, 2, 3, 4, 5, 6. And at the intersection of these, we could make dots representing the outcomes. And that's our dot diagram. And we have 12 dots. And we can see that each dot represents an outcome. This dot would be tail, 4. What would this dot be? This would be heads, 2, etc. So that every dot represents an outcome, and that might be the best way to represent the sample space. But be that as it may, in each case, the number of elements in the sample space is 12. Let's just make a note. So the sample space can be represented by a list, which is very difficult to do. A tree diagram could help us make that list. But I think the most efficient is a dot diagram. Now the question is, how could we have gotten the number 12 without listing all the possibilities? Well, let's take a look at the tree diagram. A coin has 2 possible outcomes. It could be heads or tails. So for the toss of the coin, there were two activities that could occur if that was an experiment by itself. And if we toss a die by itself, there are 6 ways that can occur. What would we do with these 2 numbers to get the 12? Well, yes, we would multiply. This is called the counting principle. So because the coin could occur in 2 ways and the die could occur in 6 ways, the total number of events when we combine these 2, tossing a coin and a die, would be 2 times 6, which is 12. But notice that the coin and the die have nothing to do with each other. All right, this is called the counting principle. Let's summarize it on the next page. So in our do now, the number of ways to toss a coin, and I'll use this notation, is 2. And the number of ways to toss a die, there were 6 possible cases. So the number of ways to toss a coin and a die would be the product, number of ways to toss a coin, times the number of ways to toss a die. And that gave us our 2 times 6, which is 12. So the counting principle says that if n of A represents the number of ways event A can be performed or can occur, and n of B is the number of ways event B can occur. If we know those individual ways, then the number of ways that both A and is an important word in math, A and B can occur, would be the number of ways A can occur times the number of ways B can occur. Okay, and this would represent the total number of ways both activities can occur. Okay, so and implies both. And I'm sure you've seen the counting principle before in many ways. Let's look at an example. All right, so I'll call this number 1. Let's say we go for lunch and we look at the menu and there are a main course, which consists of a hot or cold main course, a dessert, which is fruit or ice cream. Oh, ice cream. And a drink, which would be milk, juice, or soda. Okay. Now, how many outcomes are there in the sample space if we pick a main course, a dessert, and a drink, in that order? All right. Another way to write this is how many lunches can we pick? So here we know that the main course, there are 2 options for the main course. There are 2 options for dessert. And there are 3 options for the drink. So to pick main course and a dessert and a drink, we multiply these and we get 12. And here, it would be a little bit more difficult to list all the possibilities, but there are 12 possible outcomes as well. Okay, now let's take a look at how permutations are formed. Okay, suppose that in an 8E class, 3 students are to be seated in a row in 3 seats. In how many ways can this be done? And let's list all the possible arrangements. List all possible arrangements and in how many ways can this be done? Okay, now let's list this using a tree diagram. So the first branch would represent the first seat. So just imagine the 3 students in front of the room waiting to be seated in 3 seats. So for the first seat, there's a choice of picking Annie, Brandon, oops, my hand slipped, or Carolyn, right? So one of these 3 are seated in the first seat. Now for the second seat, we have to see who's in the first. So if Annie has to sit in the first seat, then the 2 students that are left here are Brandon or Caroline for the second. If Brandon has to sit in the front, then 2 students that are left are Annie and Carolyn. And if Carolyn has to sit in the front, then the 2 students left are Annie and Brandon. So now the first and second seats are taken by 2 students. The third seat is already determined because we already seated 2 students. So if Annie sits in the first seat, so the last branch is the third seat. So if Annie sits in the first seat, Brandon in the second, then Carolyn has to sit in the third. But if Annie's in the first and Carolyn is in the second, then Brandon is in the third. If Brandon is first and Annie's second, Carolyn is third. If Brandon is first and Carolyn is second, Annie is third. If Carolyn is first and Annie's second, Brandon is third. And if Carolyn is second and if Carolyn is first and Brandon is second, Annie is third. So notice that this tree diagram is a little bit different from the tree diagram in the Do Now. It seems that the branches go down by one, and that's because we consider this without replacement. Once one person is taken, then we cannot use that person again. So we could list this as ordered pairs because order does matter. It does matter who sits in first, second, and third. So this top branch is A, B, C, where Annie's first, Brandon's second, Carolyn's third. And similarly, this would be A, C, B. And this would be B, A, C. This branch would be B, C, A. This one would be C, A, B. And the last one would be C, B, A. And notice that this result and this result are very different. This result here tells us Annie's first, Carolyn is second, Brandon is third, whereas this one says Brandon is first, Carolyn's second, and Annie's third. So order matters. And this is an example of a permutation. And what's even nicer is that the number of ways this can occur is 6 ways, and the easy way to find out the total number of outcomes is to use the counting principle. There are 3 ways to pick, 3 students to pick for the first seat. Once that student sits down, there are 2 for the second. And once these 2 students sit down, there's 1 left for the third. And we multiply, and we get our 6 possible outcomes. These are the number of elements in the sample space. The sample space is this list. This is our sample space, whereas the number of elements in the sample space is 6, and that could be found by multiplying 3 by 2 by 1. All right, let's summarize this. This is an example of a permutation, so let's write the definition down. A permutation is an arrangement Okay, and the word arrangement implies that order matters. So whenever you see the word arranged, remember that order matters. Where order matters. And this is a special case of the counting principle. Okay, a special case. So when we wanted to seat 3 students in 3 seats, we found it was 3 times 2 times 1. If we wanted to seat 4 students in 4 seats, that would be 4 times 3 times 2 times 1. If we wanted to seat 5 students in 5 seats, that would be 5 times 4 times 3 times 2 times 1. But if we wanted to seat 100 students, in 100 seats, well, following the pattern, it would be 100 times 99 times 98, and we would keep counting down until we hit to 3 times 2 times 1. At this point, we need a notation for this very special counting principle, and that is called factorial. Okay, so 3 times 2 times 1 is represented by 3 and an exclamation point. This is read 3 factorial. And 3 factorial means 3 times 2 times 1. It's not 3 with excitement. Okay, this one is 4 factorial. This product is 5 factorial. And finally, the last one, this is where we would need the factorial, would be 100 factorial. So in general, to seat n people in n seats, we would represent this as n factorial. And that product is n. We start with n and we keep subtracting 1 from the previous one. N minus 1, n minus 2. If we subtract 1 from n minus 1, we get n minus 2, n minus 3. And these factors decrease until we get to 3 times 2 times 1. That's the symbol for n factorial, where n is a natural number. There's no such thing as a negative factorial. And 0 factorial is defined to be 1. And the reason why we do that is when we get to proofs with combinations, you'll see why this is necessary. 1 factorial is defined to be 1. Okay, that's just a side note. All right, so let's take a look at a problem. Now, with permutations, we can consider repetition and no repetition. When we seat people in seats, of course, there's no repetition. I mean, you can't seat one person in 2 seats. So here's an example of a permutation with and without replacement. Let's look at the next page. Okay, these 2 questions are on the worksheet. They're questions 4 and 5. I wrote them out just in case someone else is viewing the video. And number 4 says, how many 4-letter arrangements can be formed from the letters A, B, C, D if... Okay, now when we talk about 4-letter arrangements, the arrangements will not make sense. In other words, it won't form a word. So if we allow for repetition, then we just have, now we're going to have 4-letter arrangements. So we're going to put 4 slots. In the first case, we can repeat the letter. So I could have something like A, or maybe A, B, etc., etc. So if the digits can be repeated, then there are 4 ways to pick the first digit, and 4 ways to pick the second, and 4 ways to pick the third, and 4 ways to pick the fourth. So the answer here, by the counting principle, is 4 to the 4th. And that's because repetition was allowed. But if no repetition is allowed, just like seating 4 students in 4 seats, that's a permutation. And that would be 4 for the first, 3 for the second, 2 for the third, and 1 for the last, which is just 4 factorial. And that comes out to be 24, I believe. Okay, so sometimes permutations are mixed in with the counting principle. Let's look at number 5. Number 5 says, how many different 2-digit numerals can be formed from the digits 3, 4, 5, and 6 if a digit is repeated and if a digit can appear only once in the numeral. So we're forming 2-digit numerals. So let's make a blank space for that. And we're going to multiply. These are both the counting principle. But we have to consider how many possibilities in each case. So if we're forming 2-digit numerals and a digit can be repeated, I could have something like 33. I could have 44. I could have 55. I could have 66. But I could also have 34, 43, etc. So in this case, because digits are repeated, there are 4 possibilities for the first pick and 4 possibilities for the second pick. So the answer would be 4 squared, or 16. Whereas if I cannot repeat a digit, that's part B. I could have something like 34, or 43, or 62, or 26, or 36, or 63. These are considered different outcomes. So the number of ways that could occur would be 4 choices for the second, and once I pick the one, there are 3 left for the 4 choices for the first, and then once I pick that, there are 3 choices for the second. And that would be a total of 12. And actually, it would be possible to list all 12 possibilities. I've listed 6 of them. We have 6 more to list. I'll leave that up to you. All right, so let's take a look at something very, very important here. Let's continue on the next page. All right, I'm going to extend this problem that's not on your worksheet. How many different 3-digit numerals can be formed from this set 3, 4, 5, 6 if a digit can appear only once? So again, if we have 3 digits and we cannot repeat, there are 4 choices for the first, 3 for the second, 2 for the third. All right, now this almost looks like a factorial. And because it's very close to factorial, we cannot represent, well, we can represent it in factorial notation, but a way to represent this would be 4p3. Okay, this means that there are 4 slots and there are 3 slots and we're picking from 4. So this tells us the number of spaces and this tells us how many elements in the set. Okay, so this is 4p3. 4p2, which was the previous problem, is just 2 spaces, but we have 4 times 3. That's 4p2. So in general, the number of possible permutations when we are not taking all of them, okay, we're not taking all 4. So we say the number of possible permutations P of R spaces chosen from n things can be represented by NPR. Now, it's important to note that R should be smaller than or equal to n. And I'll talk about what happens when n and r are equal. So NPR would mean n, we start from n and we count down n minus 1, and then we keep counting down to n minus 2. But this time, we don't count down to 1. We count down to this factor. And there's a way to get to the last factor using the r. Can you find a way how we can use the n and the r to find the last factor? The last factor can be found by taking n minus r and adding 1. Let's try it. Here n is 4. R is 3. N minus r plus 1 would be 4 minus 3 plus 1, which gives us 2. And that is our last factor. In this one, n is 4 and r is 2. So n minus r plus 1 would be 4 minus 2 plus 1. And remember, we add and subtract from left to right. So this is 2 plus 1, which gives us 3. And that's our last factor. So this is the definition of NPR. NPN is n factorial, right? And if we use the rule here, when r equals n, n minus n is 0, and we are left with the last factor of 1. So NPN is n factorial. So 4 factorial is 4p4. In our previous problem, when we sat 100 people in 100 seats, 100 factorial was 100p100. But our goal is to find a rule for this using factorial notation. Let's take a look and consider what that would be. All right, so in number 6, I'd like you to compute these. 7p3, 8p2, 6p4, 7 factorial over 4 factorial, 8 factorial over 6 factorial, and 6 factorial over 2 factorial. Copy these down and take a minute to compute them. Okay, so remember, with the p notation, the r, the second number after the p, tells us how many spaces we have. And the 7, the n, says count from 7 down. So the first one would be 7 times 6 times 5, that's 7p3. The second one would be 8 times 7, and 6p4 would be 6 times 5 times 4 times 3. All right, and we could easily compute those. Now, let's try the factorials. If we do the first one, 7 factorial over 4 factorial, we write 7 factorial out as 7 times 6 times 5 times 4 times 3 times 2 times 1, and the 4 factorial in a similar way. And notice that these divide through. So our answer, I'll just leave it as 7 times 6 times 5. Okay, do the other two in a similar way. For the second one, I wrote out 8 factorial and 6 factorial, and notice that now we can divide through these, and we're left with 8 times 7. Notice that I didn't really have to write out the factorial. I could have written it as 8 times 7 times 6 factorial over 6 factorial, and these divide through. I could have done that to save myself a little time. Okay, and let's try the last one. So the last one, we could write it as 6 times 5 times 4 times 3 times 2 factorial divided by 2 factorial. The factorials divide through here, the 2 factorials, and my final answer is the product 6 times 5 times 4 times 3. Okay, do you notice anything interesting here? It looks like these are equal. So it appears that NPR can be represented as the quotient of 2 factorials. Let's see if we could get to that rule. So here, if I generalize NPR, well, now let's see. In the first one, we have 7 factorial on the numerator, and that was here. In the second one, we had 8 factorial, and that was here. And the third one, we had 6 factorial, that was here. So it looks like the numerator will be n factorial. All right, now how do we get the denominator using the n and the r? Well, the n in the first one is 7, and the r is 3, and we got 4 factorial. In this one, n is 8, and r is 2, and we get 6 factorial. Here, n is 6, and r is 4, and we get 2 factorial. It looks like we subtract r from n and put a factorial after it. This is how we define NPR in terms of factorial. And, okay, so that's what we have. And again, this would represent the number of ways to permute n things r at a time. N permute r is the way I would read it. Okay, so keeping that in mind, let's try another one. I'd like you to write 12p4 in factorial notation and leave your answer in factored form, simplified. So copy this down and try it yourself. Pause the button and try it yourself. Okay, so using our definition for NPR, we've got 12 factorial divided by 12 minus 4 factorial. So that's 12 factorial over 8 factorial, which could be expanded as 12 times 11 times 10 times 9 times 8 factorial over 8 factorial. And notice how we can divide through these two. So our answer in factored form would be 12 times 11 times 10 times 9. Okay, and that would be 12p4 if we were to do it using the factorial notation. But we could easily get this product by using the fact that we have 4 spaces and we count down from 12. All right, very good. Now let's look at another problem. All right, this next problem is number 6 on your worksheet, which says how many arrangements of 3 letters can be formed from the letters CAPSULE if a letter is used once in each arrangement. Okay, and now notice the word arrangement. As soon as we see that word here, we think of order without repetition. So we are taking 3 letters and putting them together, right? Any 3 of the letters. So we're going to use one of the letters listed in capsule, and we're going to use and make a 3-letter word. And this word does not make sense. It doesn't have to make sense. So we've got 3 spots to fill. And we have to think about the number of choices we have for each spot if we cannot repeat a letter. So let's count the number of letters we have. 1, 2, 3, 4, 5, 6, 7. So we've got 7 choices for the first. Once we pick a letter, there's 6 choices for the next. Once we pick those 2, there are 5 choices for the third. And that would be our answer. If we wanted to be really fancy about it, it would be a nice practice. We could write this in P notation. So we're picking 7 things from 7 things, and we're filling 3 slots. So this would be the total number of ways. All right, let's try another problem. Now, this next problem is not on your worksheet. You do have a similar one, which I believe is problem number 8, but it has the same idea. So let's look at it. How many arrangements can be formed from the letters in the word median if a letter cannot be repeated using, and then I have different scenarios, all 6 letters, 1 letter, 2 letters, 3 letters. And then we have this new phrase, at most and at least. And I wanted to discuss that with you before the end of this lesson. So, okay. If we use all 6 letters, because there are 6 letters in the word median, 1, 2, 3, 4, 5, 6. If we use all with no repetition, that's just 6 factorial. Now, if we use only 1 letter, we pick 1 letter from the 6. Well, we have one slot and it's 6. And of course, if you'd like, you could write 6P1. If we pick 2 letters, that's 6 times 5, and that could be written as 6P2. Not that you have to write these, I'm just reviewing with you. And then if I had to do this, I would do it with the little spaces. And then if we had 3 letters, that would be 6 times 5 times 4, which is 6P3. Notice we don't really use the factorial formula here, but that's used for later when we want to prove relationships between combination and permutations. Now, if we want to use at most 3 letters, what does it mean when So in this lesson, we discussed the counting principle, the number of ways 2 events can occur at the same time. And we said that was the number of ways the first event can occur times the number of ways the second event can occur. And we extended the counting principle to a very special counting principle called permutations, which are usually without repetition. But if we have a problem where repetition is allowed, we use the general counting principle. All right, and then we have this word or, which we will revisit again in probability. When we have or, we add these 2. And it may not make too much sense, but if I had a six-sided coin, a six-sided die, and a two-sided coin, there are two ways that the coin could be tossed and six ways that the die could be tossed. The number of ways that I can toss a coin or a die would be 2 plus 6, which is 8. And again, we're assuming that A and B are independent events. So we will revisit or, and this occurs more often with the words at most and at least. We add those numbers. So keep that in mind for the next lesson or in the future lessons, and I wish you all a wonderful day. Bye-bye now. Simple.